Hello and welcome back to the channel. It's Mark from Powersonic and Apprentice 121. In today's video I'm going to go through some dead testing and some live testing. So we're going to have a look at some R1, R2 measurements on both the socket and the lighting circuit. Reason being, I've got the sockets on an RCD, the lighting circuit is not, and also doing some live ZS measurements in an entirely safe way on both those circuits as well. Now before we get on with the rest, I've got the guys on in the background this morning, so Sam and Nick, on the Electricians Monday Club. For those of you who aren't aware of it, absolutely cracking podcast. And I appear myself from time to time, and they're having a good discussion this morning about, being off work when you're ill, and Sam's new experience in his new role. I'm only about 20 minutes in, so I'm going to get that on in the background, pop a little time lapse up while I get set up on this board, then we'll have a little jump around. I've got some of these LED lighting panels in my office space. They are on Dali controllers, so we can get all that prepped and ready as well. And ultimately the idea is some of the differences in values we will get throughout the installation when we are doing live and dead measurements, and how the calculations that you can obtain through the dead test results can really help you with understanding what the live measurements are showing you. A bit in the office, I have shown this before. We have got the water bond up on there. There's a gas meter in there as well, which is all bonded. Other side of this wall there is another supply for the loading bay area of the unit, and one of the other offices as well actually, so it's a really weird setup in this building. And we've got a three-phase head in here. You can see at the minute I've got my little TIS leakage meter on, and I'm looking at DC current for the time being that's flowing through the neutral conductor, and you can see there it's sort of around 4 or 5 milliamps. If we have a look at AC, this will just show you the current flowing in the installation. We've got about 8 amps, and primarily that'll be the electric heater, which I've got set to maximum right now over at the other side of the office because it's freezing. So we've got that there. You can see it's a TNCS head. We've got an isolator switch here. I've shown this on an earlier video before. It's a weird setup, and I think they did this to try and limit the earths of the rest of the building passing between each other. I don't know quite why they set it up like this, but there is a steel conduit between this isolator and this board, but there is a rubber grommet in there, if you like, that separates the two. So the main earth into here is only joined into this board through the earthing conductor within this. I had to explain that on an earlier video. It's very strange. It's not how I would have particularly done it myself. I think it's because we're very, very close to the TX on the DNO's side. Yeah, that's my assumption, but we'll see. That's not really our concern for today anyway. We're going to have a look in here. I'm going to get all the power off, obviously, and we can go through the dead tests. I will obtain a measurement of ZE as well, because we're going to need that. And I will also show in the calculations how by inquiry we can use that figure as well, and how that affects things, and explain a little bit about the effects that can have on, high power circuits with long distribution cabling when you're working with a small value of your maximum air fault loop impedance, and how the calculation sometimes doesn't help you with that. But we'll jump on with the video. I'll get everything set up. We'll go through from the beginning, starting with RZE in an entirely safe way, and then we'll move on with the tests. I'll jump back in a sec. Okay, so I'm all set up now, ready to perform the ZE measurement. Obviously we need to do that on all 3 phases in this instance, and if I wanted to get the value of PSC and PSC, we could do that at the intake by measuring onto the neutral as well, but I'm not going to do this in this experiment. I just want to know what the ZE is, so we can play around with some calculations later on. You'll see I'm in a bit of PPE, so I've got my helmet and face shield on, got some rubber gloves on. It is a live test, also utilising an extended probe. You can wear an arc suit if you wish. We do have them. I don't consider it necessary in this kind of setup, but if we was on a bigger supply head with more current that was possible to cause an issue, then I would take appropriate measures with PPE. And if you are doing those kind of things, you really need to be getting an arc fault specialist to come in and do a calculation on the discharge energy that's going to be available at that point. But I'm all set up with this. I'm ready to go. We have the TIS MFT Pro, which I've already crop clipped onto the earth, and as I said before, these 2 enclosures aren't actually linked in the containment. There's a separation that the original installers have put in, so I could have just probed straight on, but it's as easy to just take it out and crop clip. So I'm doing it in the right way because the earlier video I did, when I didn't take it out, there was a few questions, it caused confusion, so this prevents that. You'll see I've got the clamp meter on there, and I'm just checking that the current flowing in the earthing conductor isn't of concern. So we've got that set up ready and recording, and at the minute it's 0.1 milliamps. So there's next to nothing on there as we would expect, and it was the same on the DC range as well. So now I can get on with doing the test with my extended probe, face shield down, and yeah, let's just run through it. So again, we're going onto the live side of that switch. I'm showing 239 volts. Can hit the test button. Excuse me if you can't hear me because I am obviously behind the old face shield. And I am measuring 0.09 with an ISC of 1.94K. So if we move over to L2, and again I'm being careful, I'll save that result. Beauty of the TIS tester is it works with rubber gloves, so that's helpful. Again, same sort of voltage, 239. Hit test again, should be a similar figure. So we've got 0.08 and 2.18 Ka on L2, and if I save that and go on to L3 is the final measurement, and we hit test, and 0.09 and 2 Ka. Pop this up. So stepped away now, and yeah, it's coming out roughly 2 Ka on your single phase prospective fault current. Obviously with it being 3-phase, there's some other calculation to look at with that, so we'll jump into a bit of information of that later on in the video. And 0.09 for the ZE, you know, which is quite a low value. I have measured lower than that here before, but the DNA since then I've been messing about. There's a new screw fix and tool station opened up just around the back, and I think they've been messing about with their supply transformer and whatever's been going on there, I don't know. So it's affected the values in here. Yeah, so that's how ZE. I can pop this back together now and cover up those live parts, just shut the enclosure front, and then we'll jump on with doing some dead tests where I can take this PPE off and we'll run through the entire process start to finish and look at the calculations. Okay, so we've got the board safely isolated now. I've put a little lock on, you know, just in case. Obviously there's only me in here, but you never know, you can knock things by accident, so that's can't be a possibility now. So we need to get our end-to-end resistance on the ring vinyl circuit. It is a 4mm with a 1.5mm CPC, so it's 4mm twin and earth. The value should be quite low because it's not a massive ring. There's 1, 2, 3, 4, 5, 6, 7, 8, 8 or 9 sockets on it. This is just my office, it's not a huge circuit. So we can get our end-to-ends, make the crossovers, zip around the ring, there's no spares. We should get the same values for our R1, R2s at every socket outlet. But before we do that, we'll just quickly gather the end-to-end data. I have also already linked out the line and CPC on the lighting circuit, so that's ready to go and take a measurement over at the end point of this lighting circuit, and we'll show you that in a second. But I'll just run through the end-to-ends. I've already cropped onto the CPC, so we'll do that one first. It's 0.34 on CPC. We would expect the lines and neutrals to be lower because they're larger conductors. And it's 0.13, and again your maths, if you get into this habit of 1.67 times with your typical twin and earths, it won't work on this occasion because we have a 4mm line and neutral conductor and just a 1.5mm CPC. But if we jump onto the neutrals, they should measure out at the same value as the lines, and they do exactly, so it's 0.13. So I'm happy with those now. We can make the crossovers in the board. I've got my little jump leads to do that. We've got these, it's going to add a little bit of resistance to the circuit, but not a great deal. And then I can zip around and go and get my R1, R2 at the sockets, and I'll show you doing that in a minute. And then we'll jump up and get an R1, R2 on the lighting circuit, get all this lot dressed back away, and we can take our live measurements. So I'll just jump these over now and I'll show you me getting the R1, R2s. Okay, so I've got that all jumped over now. There is a little handy socket here at the side of the distribution board, so I can gather an R1, R2 off this, and if I hit test, it's coming out at 0.13. Now I've already been over the other side of the office and checked that, but I'll just spin you around and you can have a little look at me doing it. I'll get it set up for when I'm going to do the lighting circuit. Saves messing about with the camera. So I will show you me getting that at a couple of other sockets as well. One thing to do with your R1, R2, it's always worth checking at both sides because you can get high impedance points through your socket fronts, especially on older ones. So at that stage I'd be checking both sides as well, just to make sure you've not got an issue there on the socket front. But yeah, I'll spin you around now. We'll get set up for the lighting test and I will show you at the sockets for the other R1, R2. It's going to be a bit shaky camera work, but I'll try my best. I've hit the test button and we should come out with a similar value. If I show you on there, it's 0.12. It's the same on all the other sockets, so let's get on and have a look at the lights and I'll show you a measurement up there as well, doing the dead test. Okay, so you might be able to see that I've wired in this little Q-Tech adapter. So this is end of line. You can see the last feed coming into this light fitting. It's into these are just push fit connectors in here. I've closed it up so we're ready to do the live measurement as well quite safely. But it's wired into line, neutral and earth. So if I hit the test button on this now, it's going to give us an end-to-end value of the R1, R2 on this circuit, and you can see it's 0.5 ohms. So we have that measurement now. It's all saved in the test instrument, so we can play around with the calculations once we've obtained some live measurements. And as I've shown before on other videos, we can get a live measurement of ZS quite safely at all the socket outlets. And now, because I've wired this in here at the dead test stage, we can also do that very, very safely with the Q-Tech adapter, no access to live parts, because no one wants to be up the steps with probes messing about on live terminals unless you absolutely have to, and in 99% of cases you do not have to. It's one of the things I want to keep getting over to people, that this is a valuable test measurement we can take. It helps us understand parallel paths in the earthing system and the effect they're having on the installation, and it also ensures that we haven't made any mistakes during the dead testing, because as you've seen, I've had a lot of that bought apart now, so I can go and put all that back together, and it's a final check that after all of that we have electrical energy at the light fitting and an earth path that's safe. So I'll go and get on with tidying the distribution board up, get the power back on. I might as well leave all this here because I can come straight back to it and get my live measurement. Just bear with me 5 secs. Okay, so we've got the power back on now. You can see I'm quite safe. I've got my little test lead in there, wired into the light fitting. I'm measuring 239 volts. I can hit the test button. It's going to give me a value of P, FC, and also a value of ZS, and you can see I am getting a ZS of 0.56 and a PFC of 0.3 kiloamps, which is sort of what we would expect. It's given me a thumbs down on the test because I've left it set up for if it's 100 amp views, so that's a feature of that. Let's redo that because that's quite interesting. If I change it to an MCB, what it is, it's type B, and change it to a 6 amp, save all of that, the TIS test set should now give us a different result on the screen. So you can see there it's given us a green thumbs up. So that's really quite clever. It's making you aware as the tester that you might not have inputted all the required data into the instrument, and the value it's recorded isn't acceptable based on the circuit protective conductor protective device it's expecting. So you can see in this case our ZS is 0.56 ohms. We'll see how that plays out with the calculations based on our ZE and our dead testing, and also what the PSC is at this end of line on the lighting circuit. Let's jump down and do some of the measurements on the socket circuit. I can pop all this sealing back together. Obviously I've got to turn the power off while I then open this live parts. I don't want to be exposing myself to any unnecessary danger, so I'll do that, unwire this adapter, put the sealing back together, and we'll get some ZS's on the sockets. Just bear with me a sec. Okay, so we've tested the lights now for our live ZS measurement. Can repeat it for the sockets. It's important with the sockets you go all the way around the ring because you will get different values with your ZS measurements. They won't be the same like they were during the R1, R2. I'm just going to demonstrate at this socket and I'll quickly run around and get the highest value. If I switch that on now, you'll see in the loop impedance measurement I'm getting 239 volts between line and earth and line and neutral. Important now that I set it to no trip on the RCD range, because we do have this RCD up there looking after the socket circuit, and I'll speak a little bit about that in just a minute. But if we get the test result from this socket, just so you can see me obtaining a result at least 1. Now obviously when it's doing the measurement for earth fault loop impedance through an RCD, we know that they can increase the value that we're recording due to impedance in the RCD itself. Some are worse than others. But on this one, you can see I have measured, that's coming across on camera because the lighting's not that brilliant here, but it's 0.46 ohms for the line to protective earth, and it's measured 0.17 between line and neutral for the impedance as well. So when you carry out this test, it gives you that information, which is good, and also that we've got just over a kiloamp of PSC. So we've got that on there as well, and we've got near enough 0.4 kiloamps on the line to earth via PFC. I'll jump around the ring now. I'll go and get those values for the other sockets. I'll make a note of the highest value, and then we'll have a look at how all of this pulls together by using calculation, test results, and some of the reasons that we might have seen some differences in both those things. Just to talk about this RCD, so up there that is a type AC RCD. Now I've got my little DC leakage meter here, and if I go on to L2, which has just got the sockets on, so you see here we're on L2 and only the sockets are on there, there's nothing else on that phase. So we know that's what we're measuring, and it's giving me a DC leakage value, so there's circulating DC currents of about 3 milliamps. So that's not to sniff your nose at, and I've measured this dip above sort of 10 to 15 milliamps. Obviously I've not got any of the computers switched back on or anything like that. Basically the only thing that's running right now is the router for the internet and the telephones. Everything else is off. So I suspect as I was to turn things back on, that would creep back up again. And the interesting thing I've observed is every time I press the test button on this, it's been operating. If I do the RCD tests on it, it works just fine. So this is just my observations, because obviously we know now with the introduction of type A RCDs that perhaps historically where we haven't had faults with DC equipment leaking excessive DC currents into the AC system, it's maybe not been that big of an issue, which is why we've had protection from our type AC RCDs. For decades it's worked quite well. I think they're one of the devices that got introduced that definitely did increase safety within domestic premises, certainly, especially due to some of the standards of workmanship that we've seen floating around. And yeah, it's just an interesting observation. So this new TIS meter, I'm going to play around with this quite a lot more now on most of the installs we're going to. I'm going to be checking what sort of values we're seeing for typical DC circulating currents, and I'm also going to be checking the AC leakage as well on installs. Measured it here today and there's basically none, unless I've got the computers turned on. As you'd expect, they naturally leak a little bit. Yeah, so we'll keep up with that one, but I don't want to divert away too much from the purpose of this video, which is talking about your dead measurements and then your earth fault loop impedance values. So I'll just go and get that highest value on the sockets, sit down at the desk, I'll write all this out, and we'll run through the numbers. Okay, so I just realised I recorded all of that with my microphone muted. So I've turned that on now. Hopefully everyone can hear what I'm saying. That's annoying because it was like 6 or 7 minutes and now we've got to repeat it again. But there you go, that's the beauty of YouTube. You'll see here we've got the Napit desktop opened. I've put some of the characteristics of the circuits in, so the number of points, the size of the conductors, and the protective devices at play. And if we go through the lighting one first, so we've got a B10 with our max ZS of 3.49, so quite a generous figure to shoot at. And our dead test measurement was 0.5 ohms, so that was where we joined over the line in the CPC and the distribution board, went to the end of the circuit and recorded a value, and we actually measured 0.56 with the live measurement again up at the light fitting. So if we look at this now, we can see on the light circuit, if by the calculation we'd have a figure of 0.58 ohms, we've actually measured 0.56, so they're near enough the same. You have a difference in tolerance within the test instrument as well when you're making your loop impedance measurements. I think it's about 10%. So that's a factor. We've also introduced the bonding connections as well with the live measurements. So we've got water and gas services that are both metallic into this unit, so they're going to have an impact. There's no other parallel paths because the trunking and containment doesn't go back to the consumer distribution board. It's separate, so it's not really providing any means of additional CPC factors into the circuit, so you're not going to see any of that. And yeah, that's just an interesting observation. The one thing it does prove to me is that having had the board apart to do my dead tests, I haven't clamped down on any sleeving within that circuit or pushed it back behind the earth bar. We're all capable of a mistake, and it's a final check that I've put that back in the right place and that we have a safe system to hand back to the client. That's the primary reason for doing a ZS, and it's one of the reasons I'm trying to demonstrate you can do it quite safely. It's giving yourself that added insurance that you are handing over safe electrical systems to consumers, and that's really important when understanding the electricity at work regulations. And people often hold up Reg 14 as to why we shouldn't be doing unnecessary live working. There are other regs in there where we have to ensure that electrical systems are safe for other people to use, and it's an important way of verifying that. That's my 2 pence on that. But yeah, if we look at the socket one now, and again there's a couple of bits of maths we can do with that one. So we've got little r1 and little rn of 0.13 and little r2 of 0.34, and then our r1 r2 figure of 8 value, so that's where you cross your line and your CPC over from leg to leg of the ring, is 0.13. Now typically we have this 1.67 figure in our minds from 2.5mm twin and earth excuse me, but obviously this is a 4mm twin and earth cable, so those maths don't play out. Someone has also introduced a short length of 2.5mm earth cable for whatever reason into the first socket of this circuit, so that's going to skew those bits of maths there as well. But we'll focus in on the actual measurements of your R1, R2 via calculation through dead test, and also the measured value. So we measured 0.54 on the socket circuit, and the calculation shows us it should have actually been 0.21. So that's because of your ZE at 0.08 and your 0.13 R1, R2 added together. So we've kind of got a difference of around 0.3 ohms, and that can sometimes lead you to think you could have clamped down on some earth sleeving, perhaps missed one of the legs going back into the earth bar. But in this case, it's because we have another introduction to our circuit that isn't there for the lights, and that's the RCD. And they are known to increase the value of impedance we measure with an air fault loop impedance MFT tester. It's just the way that they collect the result, because obviously they can't trip the RCD because it would remove the source of energy and we wouldn't be able to take any measurement. So there is that in there, and that kind of explains that difference on that particular circuit. And as long as you understand that, you can still get the same verification that all of the conductors have gone back correctly into the distribution board, all of the earths are back in, there's nothing been left in the wrong place, and we've got an acceptable value there recorded. Now I have chucked into the mix there, you'll see I've put in, just for argument's sake, that there's a motor on L3. There isn't, it's a water heater, but we'll pretend just for a second, and you can see if I was to have a D63, so it's a bit of a beefy motor, long cable run, the maximum value of ZS we're allowed on that at 80%, and obviously the 80% is the rule of thumb figure we work to because the conductors are up to operating temperature, is giving us a maximum ZS of 0.13. So if we was to take our ZE by inquiry, I'm just pretending again that this is a domestic TNCS system, you know, you'd have 0.35 if it was TNS, 0.8, so if you don't take that measurement straight away, there's no size of conductor you can use that's ever going to make that circuit comply. So that's one of the reasons it's important that you actually take a measurement of ZE. You know, if this was in a larger industrial environment, for example, and you could have other parallel paths through trunking systems, conduit systems, perhaps other supplies into the building as well that are all going to help lower that impedance path. You know, there's helpful facts there when you actually record an earth fault loop impedance measurement that might lower your value below what you can actually do through the calculation. And I will say, if you were designing a circuit, you would never want to be relying on your parallel paths to bring that value into compliance. But if you were on an EICR, for example, you know, you can, if you're lucky, you'll have the information from the original design which will show you what the impedance was at that point, so the recorded value of ZE. And you've seen in my unit here, I've recorded different values on different days. It's not a set figure, it does move around due to what's going on in the distributors network. And then you come along and do your ZE measurement and do your calculation, and that figure can actually be above what's allowed. If you then put that into a report without recording a ZS, for example, you're not really handing over enough information to a duty holder to be able to make an informed decision. Really that's a measurement that you should be taking, so you can give them that information that actually, we've seen a change in the value of ZE through our live test. We've now done our R1, R2 measurement, and when we do the calculation, we're above the maximum ZS allowed on that circuit. But when we've gone and taken a ZS measurement, because of fortuitous parallel paths, if I can get those words out, the circuit still complied. It would still operate in the event of a fault, and the duty holder can then make a decision if they think they want to be doing remedial work or not because of that, and you can code accordingly within your report. But the fact we've got a box there that allows us to record a value of the maximum measured ZS, if we put it in there, again, it's total insurance and compliance, and the duty holder and us as the test and inspector have all of the relevant information to hand to make an informed decision. It's called engineering judgment, and you can quite safely and easily obtain those values in 99% of cases. Now, obviously, if you've got something like a chemical plant or a petrol refinery where they don't want to be doing live test measurements for obvious reasons, unless the whole plant's shut down, the calculation method is a viable, and you can only go so far, can't you, in those environments. So I'm not suggesting for any 1 minute that you should be doing live testing everywhere, but you should be aware of the importance of doing it, the value it can add to your reports, and the extra layer of safety and assurance you can bring to your clients. And there's been a lot of apprentices and electricians messaging me saying they've never been shown or taught how to do live testing at their colleges, because it's always thrown up, well, regulation 14 doesn't allow us to do it, we're not allowed to do unnecessary live working, when I've shown you can do it in a way that will limit any exposure to any live terminals. And I think if we teach people that, they'll have an understanding of how to do it safely, so when they're stood in that situation where they do need to record a value of their fault loop impedance, and there'll be occasions you have to do that anyway because of manufacturer instructions or a specific work environment you end up being in, be rail, military, healthcare, they're going to know how to do it, and they're going to know how to do it safely. So that's the purpose of my little series of videos here with this, is to show you how calculation will play out and give you figures that are valuable and can help you, on small domestic and small commercial. If you just want to use the calculation method and you've got a team you trust to put the conductors and terminations back properly, perfectly acceptable. It's in guidance note 3. You don't have to go and record the live measured value if you don't wish. But if you do want to do it and have that extra layer of assurance for yourself that you've gone to every possible step you can to ensure you comply with EWR 1989 as best you can, and other standards that are relevant to electrical systems we're handing over to end users, then hopefully some of my videos will help you be able to do that safely. Even my guys, Matthew went off and did his 239 one. Matthew and Nathan both in their colleges, they're not shown live testing. It's just said, well, we don't do that, we do it via calculation to try and limit exposure because of Reg 14. That's the method we teach in colleges now. That's a bit of a worry for me. I think that's kind of de-skilling, and it's hiding behind a regulation when it doesn't actually apply. It doesn't, because you can take that measurement quite safely. And my opinion is we need to show people how to do it safely. You don't have to be up your steps with probes wafting around all over the place. You don't have to be taking measurements with motors running, as was suggested on this thread when I've been discussing this on social media. That's just insinuating stuff to try and diminish my point of view that we often complain of de-skilling in the electrical industry, and I think this is another one of those instances. Shoot me down in the comments if you disagree. It's just my opinion. I'm not saying anyone else is wrong for having a different opinion. The debate always brings us to a conclusion that helps everybody, so let's have it. If you've got anything to say on that, drop it in the comments. I'll happily discuss it with you. I hope you've enjoyed this video and it's been of some use to those of you who maybe haven't had experience of earth fault loop impedance via calculation and testing. And I know there's a lot of apprentices who follow me, so for seasoned sparks who have got this content thrown out on my YouTube channel at you, it's really not aimed at you. It's to try and help those guys and girls who are on a learning journey, and also some of the new electricians who come into the industry and perhaps not had this training given to them through the course of their apprenticeship. So hopefully that helps. Get involved in the comments. Thank you for watching. I will see you all on the next video on my little YouTube channel. Catch you all later.